Hello, everybody. My name is Christina, and we're pleased to welcome you to the Washington Labs Academy webinar series. We hope you find the next hour or so useful and informative. We've developed our webinar series to deal with some of the technical and administrative issues that our customers face on a day-to-day basis. We recognize that engineering challenges can be complex. We're always looking for ways to support the technology industry. Before we begin, I want to go over a few housekeeping details. First, I hope everyone is able to see the title slide on their computer. We've muted everyone's microphone to keep the meeting quality as high as possible. Recording of the presentation is underway and will be sent to all attendees. We will go through all the questions at the end of the presentation as time permits, and a full screen view may be preferred. Your selection at your computer can be done using the menu panel. In the menu on your screen, go to View and then select Full Screen. We estimate that the main bulk of the presentation will take about an hour, and we will allow some time for questions at the end. We'd like to hear from you. You can contact us via phone or email, or you can contact our presenter directly by sending your email to mike@ycsllc.biz. And now I'd like to introduce our presenter. Mike Young was the founder, president, and chief technical officer of YDI Wireless, a publicly traded company that designed and manufactured broadband wireless data communication equipment and systems. He designed and his company manufactured a complete range of wireless data communication products and accessories. YDI Wireless was a world leader in providing extended range, license-free wireless data equipment that included Wi-Fi, as well as turnkey long-distance wireless systems for applications such as wireless internet, wireless video, wireless LANs, WANs, and MANs. He semi-retired in 2004 and started his own engineering company, Young Consulting Services. He also went back to teaching college as an adjunct professor at George Mason University, where he created and taught their new wireless communication course. He also was faculty supervisor for the ECE Senior Engineering Design Capstone Program. Currently, he is an adjunct professor at the University of Central Florida and is offering the wireless course he created to the Computer and Electrical Engineering Department and still offers engineering design services. As a side note, he's also a pilot and certified flight instructor and enjoys flying his own plane, mostly doing dog rescue flights. So without further ado, I'm going to go ahead and turn the presentation over to you, Mike. Hi.
Good morning, and good morning everybody in the West Coast, and afternoon for people who are over here in Eastern time zone. So let me just get this set up so I share my screen. Just give me a second here, monitor 2. And so here we are. This topic is about broadband wireless devices. It's quite extensive. I cover a lot of material. I'm going to do my best to get it all covered by the hour, but we'll have to go through pretty quickly through some slides in order to make that happen. I want to get my little pointer up because me without a pointer is not very effective. So I think I'll use the laser pointer, and there that is, and now I'm annotating. Let me just get rid of that there. Oh, got rid of it. Okay, so, all right, so, broadband wireless. Well, back in 2004, WiMAX standards broadband meant having instantaneous greater than 1.5 megabits per second. Well, that was considered real fast back in 2004. It certainly ain't very fast today. The FCC recently redefined the definition to mean a download speeds of 25 megabits per second and upload of at least 3 megabits per second. Mostly they did that for the cell phone industry. Then there's a whole bunch of equipment out there, a lot of broadband wireless systems at a point-to-point that easily exceed this definition. We're going to be talking about some of them and the frequencies and the spectrum they used and some of the other uses of these equipment. So there's basically two types of broadband wireless systems. There's licensed wireless systems, which are cell technology and PCS systems. And there's also a licensed point-to-point microwave links on 6, 11, 18, 23 gigahertz and other bands. But there is also a lot of license-free radio bands. And the important ones are the 2.4 and 5 gigahertz Wi-Fi band, the ISM band, that's industrial, scientific, and medical band, 900, 2.4, and 5.8 gigahertz. The millimeter wave bands, 24, 60, 72, and 80 gigahertz. White spaces on UHF TV channels. I don't even know if you're aware of that. It's sort of playing in the background. And then the Citizens Broadband Radio Service. Really, on 3.5 gigahertz. Got some interesting news about that in this presentation. We're only going to talk about the license-free bands today, primarily because talking about licensed cell and PCS systems and microwave point-to-point links, there would be presentations unto themselves. Plus, I'm pretty much more familiar with the license-free band technology because that's what I did for many years in my company. So what is Wi-Fi? I don't know if you know that or not, but it really means wireless fidelity. It was set up in 1999 by the Wi-Fi Alliance. They certify 802.11 wireless LAN devices. Basically what they do is, if you got a device and you want to get the old famous certified Wi-Fi logo on your equipment, they run you through lots of tests to make sure you're compatible with other Wi-Fi devices and you meet all the standards. Once they give you that stamp of approval, which costs a lot of money, some manufacturers didn't even bother doing that, then they'll allow you to put that certification stamp right there on your equipment so that you know you're compatible with the 802.11 standard. And now, something new, WiGig, which was certified by the Wi-Fi Alliance to offer extremely high data rates on the 60 gigahertz band. We'll get to that in a little bit. So the license-free radio bands, 902 to 928, 2400 to 2483.5 megahertz. The UNII band, the 5725 to 5850 megahertz band, 24 gigahertz, 60 gigahertz, 72, 89, and 90 gigahertz bands. These are the bands that lots of people make equipment for. The 802.11a, AC, B, G, and N, they operate in the 2.4 and the UNII bands. And the IEEE 802.11AD, yes, AD band, operates at 60 gigahertz. We'll talk more about that later because that's an up-and-coming band. So the protocol was ratified like this. 802.11 first came out, frequency hopping direct sequence spread spectrum, 2 megabits per second on 2.4 gigahertz. And then he said, well, if we do CCK encoding, we can get 11 megabits per second with the same occupied bandwidth. So then that's when 802.11b came out. And then 802.11a came out. They said, boy, OFDM is really a great modulation technique. It handles multipath interference and frequency selective interference, you know, where you get gaps in your band because of multipath interference. We could do 54 megabits. And they put it on 5 gigahertz. They said, well, that came out first. They said, well, we got to get this down on 2.4. So 802.11g came out after A because we had to figure out how to make it compatible with direct sequence spread spectrum 802.11b and also upward compatible with 54 megabits per second. So that's why A came out before G. And then 802.11n said, hey, why don't we combine channels and give us more throughput? Great idea, and that's what the N does. And then we have 802.11ac, which combines even more of the channels together to get 1.5 gigabits per second, which is really fast, but that's only on the 5 gigahertz band. And then we got the 802.11ad, which is a brand new, and it is operating on the 60 gigahertz band, and they do OFDM, BPSK, QPSK, 16 QAM, and if you're running OFDM, you get 6.7 gigabits per second, and boy, you need fast processors to push that data through, absolutely. So this is the conclusion or the overview of all of it in a visual format. We start off with the wireless LAN higher level 802.11, and then we have .11, which came out in 97, .11b, .11a, and under .11a, there's .11g, where they moved it down to 2.4 gigahertz. And then we have .11n, which supports 60 megabits per second with a 4x4 MIMO. Just about nobody runs 4x4 MIMO. Maybe access points do, but clients typically don't. And then they have 20 and 40 megahertz bandwidth on 2.4 or 5 gigahertz channels. And then 802.11p, I'll bet you never heard about that. That's a 10 megahertz channel at 5.8 gigahertz for vehicle access for Vehicle environment, wave, interesting. I don't know who's doing what with that. I haven't seen much about that, but it may be coming up with these auto-driving cars these days. And then there's 802.11af, which is the TV white spaces. And that's the specifications, license-free band, mind you, on TV white spaces. That's unused VHF and UHF channels. So underneath 802.11, we have 802.11ac with very high throughput in the bands less than 60 gigahertz, and then 802.11ad, which is our wireless gigabit, Y-gig, and very high throughput at 60 gigahertz band. So this is a good chart that you could look at down the road if you wanted to see where all the various .11 N stuff and .11a stuff lives. The other thing is some people say Wi-Fi on their products, but if it doesn't support an 802.11 something specification, it ain't Wi-Fi. I see products out there where they say Wi-Fi and it's not Wi-Fi. Now, the thing about 802.11g, of course, is it operates at a 20 megahertz band with actually 22 megahertz, and you can only have channels 1, 6, and 11. And this is the main problem when they came out with 802.11b and also, of course, G, is a lot of customers said, oh, I have 11 channels, and they put one access point on channel 1, one on channel 2, one channel 3, and they were not educated over the fact that you can't do that because these channels operate over a wider bandwidth, and that was a problem, but ultimately the industry got wise and everybody went on 1, 6, and 11. However, well, keep going on here. The 802.11a came out then with the various data rates. I'm not going to go over the details here, but basically you start with BPSK, which is the lowest order of modulation that gives you the best SNR and a very good coding rate of 1/2. And then they went, if you got a good SNR, then you would go BPSK, QPSK, 16 QAM, 64 QAM. And the difference between 48 and 54 megabits per second is simply the coding rate. They do less encoding of redundancy bits at 54 megabits per second. And then they do it 48. By the way, the coding rate basically is the data bits divided by the total bits sent. So in other words, if you have a 102, a 1/2, typically they say 1/2, sometimes I see 0.5. That's really not a good way to express it. 1/2 means I'm sending one data bit for every 2 bits sent. But if I'm running from 6 to 9 megabits per second, I'm sending 3 data bits for every 4 bits transmit. In other words, 1 in every 4 bit is a forward error correction bit, and that's one of the benefits of OFDM is the ability to have forward error correction where you send enough information so that if a bit is lost, you can recover it. And that's 802.11a, and then .11g uses identical spec, but on the 2.4 gigahertz channels. For those who are technical and would appreciate this, we've got the spectral mass required to pass 802.11 specifications. So the occupied bandwidth here is where the signal level is down 20 dB, and then I have this shoulder here where you got to be down 20 dB at 11 megahertz opposite side of the center frequency, and then you have to be 28 dB down when you're 20 megahertz opposite side the center frequency. And this is an 802.11ag OFDM signal, occupies 22 megahertz. But if you use your bandwidth as negative 20 dB for the reference, then it's only 11 megahertz wide, sorry, 22 megahertz wide occupied bandwidth. Now, it's interesting because one of the things we made external amplifiers for my company that I designed for use with 802.11 devices, and there were lots of people making amplifiers. None of them really were FCC certified. Ours was because they were not linear enough. If you want to put out a 1/4 watt of effective transmit power, you need to have a 1 watt linear amplifier. It's got to be able to put 1 watt out. You need about a 6 dB overhead in order to prevent compression taking place, because if you have compression taking place, you're going to get lots of bit errors. And not only that, you'll just blow outside that spectrum mask and never get it FCC approved. So that's just a little bit about the occupied spectrum for 802.11a and G. And the other thing is about 802.11a, they said, you know, we really screwed up down on 2.4 gigahertz, so let's not give them all the channels. Let's put 20 megahertz channel spacing So like this frequency is 5180, and then we add 20 onto that, we get 5200. We add 20 onto that, we get 5220, and so on. And we can actually get 8 channels on the lower and mid UNII bands, and then another 4 channels on the high UNII band, and we can get 12 non-overlapping channels. This was really a significant improvement because the main problem with Wi-Fi on 2.4 was, and still is, too many overlapping channels. Channels 1, 6, and 11. You go to any given location, you do a spectrum analysis, you see 2 or 3 or 4 or more access points on one channel, and they're jamming each other. I've seen this over and over again. So that's why whenever I go anywhere, I see if they have a .11a or a 5 GHz channel, I go on that band, and if it's designed right, then I won't get any overlapping channel access points jamming me or others. But sometimes I still go to places, even universities, and I see in any given area, like the Student Union building, I see, my God, they got 3 access points on the same channel. Wake up, guys, spread them out. And I tell them that when I see it. So now here's 802.11ac channels. They said, wow, we got all this processing power in these DSP chips. Let's start combining frequency spectrum. So initially we had just the 20 megahertz spectrum, as you could see here, on the lower UNII and the mid UNII. And oh, by the way, there's weather radar here, but I think it's not just weather radar. Somebody told me it's the Patriot missile system, but that's rumor. And then we have the ISM band up here. And they actually have channel numbers. I don't know if you're aware of that. You know, you have 1, 6, and 11. Well, guess what? When you get to the lower UNII band, you got channel 36 and 40 and 44. So there's still 4 channels in between here, but they really don't publish it as a frequency you can tune your radio to. And it goes all the way up to channel 165. That's why sometimes when you look at your configuration for your router, your wireless router, it'll ask what channel you're on in the 5 gigahertz band. Then they said, well, let's combine 2 channels together and double our bandwidth. According to Nyquist, you double the bandwidth, you double the data rate. And so they've done that. Say, hell, let's combine all 6 channels together and get 80 megahertz bandwidth. And wait a minute, let's combine all of them together and get 160 megahertz bandwidth. And in fact, let's do this. Let's use some down here and some up here and some over there and some over there. So that's what 802.11ac gets you, and that's how they can boast extremely high data rates, is because they have so much spectrum there and they can just bind the channels together. Of course, when you start binding the channels together, you open up your receiver bandwidth and your receive sensitivity goes down, and so you probably can't get the same range with a 160 megahertz channel as you will with a 20 megahertz channel. So here are the spectrum maps for 802.11ac. I won't go over them, but basically they show where your cutoff points are, and your spectrum has to fit within these 2 things for a 40 megahertz channel and 80 megahertz channel. This is just reference. I'm not going to go into detail on that. Shows how the bandwidth resolution should be for the video and the resolution. So now just appearing now. Last year it was a dream, but now it's just showing up. 802.11ad operates on the 60 gigahertz band. 2 gigahertz RF spectrum is available. 2,000 megahertz. That is amazing. So you can get very high data rates, up to 7 gigabits per second, but very short range. What, maybe several yards indoors? I haven't actually done any tests with this because there's not really much equipment available, although we did have a 60 gigahertz point-to-point link back in the YDI days, but that was like with a 44 dBi gain dish antenna, which we could go several hundred yards. We'll talk about that later. So it's organized by the Wireless Gigabit Alliance, known as WiGig. Again, the concept is if you're going to make a device, you better make it support the 802.11ad specification. And they have that cute little logo here, this WiGig logo. And basically, a WiGig tri-band enabled device will operate on 2.4, 5, and the 60 gigahertz band. So 802.11ac intends to provide house-wide or office-wide wireless LAN connectivity, whereas 802.11ad is all about short-range interconnectivity between your devices, like your laptop and a docking station, or a smartphone, or a 4K TV. And using beamforming, which is easy to do, they can make narrow beams in the 60 gigahertz spectrum, allows other products or even other uses on the same channel at the same time in many areas. The wavelength at 60 gigahertz is 5 millimeter or 0.19 inches, about the size of your pinky nail unless you've got a big hand. So you can imagine how many dipoles you could set up and all kinds of phase arrays so that you can do steering and talk to this guy and simultaneously talk to that guy. Because the darn thing is so small, you can get a patch antenna the size of a postage stamp. Being part of the Wi-Fi ecosystem with the tri-band solution also means that you can do handoffs between 60 gigahertz and the other Wi-Fi bands. So just as a data point, or so FYI, these are the frequencies that 802.11ad supports. The center frequency 58.32, and a minimum and a maximum frequency of 57.24 and 59.4, and you get 2.16 gigahertz. Basically, they said if we give us 2.16 gigahertz bandwidth, we can have 4 channels up there at the 60 gigahertz band. So another interesting thing is the WiGig allowance is an adopter of the HDMI Licensing LLC, which holds the license to all HDMI interfaces. Therefore, the WiGig Alliance can provide equipment that supports WiGig Display Extension, WDE, which you might be seeing in the future, for supporting HDMI mapping. Now, I don't know about you, but every now and then you go, yeah, I need an HDMI cable to connect my laptop to this monitor or collect my cable box to another TV screen. Well, I'm predicting that's going to happen is they're going to start shipping TVs with WiGig stuff, with WiGig radio devices in it, and laptops with WiGig devices in it, cable set-top boxes with WiGig device in it. You just put your TV on and power it on, and bada bing, you've got HDMI from whatever you're driving it. That'd be so cool because then I can come in with my laptop computer, sit it down, tune in Netflix, and put it up on my big 55-inch screen. I mean, with no wires, I just sit it down, and there it is. I'm talking. I think that's where they're going with this, and that's a big market. I'm telling you. I'm just waiting for it to come out. Well, it hasn't come out yet. So WDE is the only 60 gigahertz specification that defines a framework for connecting to DisplayPort monitors and HDMI TVs, enabling applications such as wireless video transmission of compressed or uncompressed video. So the reason I'm talking about this is I'm predicting you're going to see this probably by next year. Stuff like this is going to come out. So here's some of the hardware. So using beamforming, okay, we already did that one. Being part of the Wi-Fi, I already did that one. Should take them out here. But they came out with the first 802.11ad tri-band wireless router. TP-Link makes it. It looks like that. It's about $300, $350, depending where you're buying it from. And it's got 802.11a, B, AD, AC. However, there's no client devices available yet. I've searched the web. I can't buy anything that I can plug into to take advantage of the 60 gigahertz band from this device. So what's the status of that? Well, it turns out that there are development kits for tri-band wireless devices 802.11ad, like from Intel, Qualcomm, Atheros, previously Velocity, Paraso, never heard of them before, but they have this little USB card over here you can plug in that's got their WiGig chip on it. And they have the mini PCI card, and they got this thing here that you can go to a little patch antenna. And so what they're doing is making available to manufacturers chipsets and solutions so they can start incorporating them into their devices. These are just a few. There are a few more out there as well, but these are the ones that popped up when I did the search recently. All right, so now that's all indoors, short range. What range? I don't know, maybe as far as you can shoot a spitball, I guess. I mean, you know, yards, maybe, because free space loss is heinous. No propagation through any kind of walls. It's the kind of thing where you sit it on the table and your computer's across, you know, your computer's on the table and your monitor's maybe, you know, 10 feet away at the most, and you got connectivity. That's the kind of range we're talking about here. And of course, the access point here, this thing has to have really fast processors to throw that data out at that data rate, to process the signal coming in and convert it to bits and send it out. I mean, even a GigE Ethernet port ain't fast enough. So if you could transmit it several gigabits per second, if you only have a GigE interface, well, you're only going to get max GigE data rates. So it'll be interesting how that plays out. Now, license-free outdoor bands, that's a whole different ball game. So who really cares about the non-Wi-Fi uses of the license-free band? Do you? Who cares? Well, lots of folks do. Consider the key features of all these license-free outdoor broadband links. First of all, they can be deployed immediately. You can get them, put them up, they're on. You don't need an engineering survey or an FCC application like you do for a licensed radio band, which takes time. You got to get an engineering firm to, get the latitude, longitude, find out what's around there, give the beam with the EIRP and all that information regarding your system in order to get approval to operate on a licensed point-to-point or point-to-multi-point band. So you need to do that. It's already FCC Part 15 certified, and you don't need to dig trenches or cables. Let's say you got two buildings you want to connect together, and you want to connect your network from one to the other. If you call the phone company up and have them drop a fiber optic cable, you'd be paying for that forever. But if you can get access to a roof or a window that you could shoot through, you can get connections in multiple megabits per second and not have to pay anybody anything. So there's no recurring cost of lease lines, and it pays for themselves typically in months, depending on the band and the data rate. And that's why there's a good amount of equipment out there. And a lot of people don't even realize that they can get this license-free equipment with directional antennas and provide connectivity between the buildings in their operation. And it'll be there as long as you need it. It'll just stay up. But then, of course, what's the downside? Anytime you have good things, usually something bad things. Well, in this case, the risk you're taking is that you must tolerate interference from any other systems, license-free or otherwise. So if you start getting interference from someone else who set something else up, well, you have no recourse in terms of legal. I mean, there's technical things you can do, change frequencies, change the polarization of the antennas, even change radio bands. There's lots you can do to solve those problems. The other issue is the EIRP power limits the range, meaning you can't put as much power as you want in to get the maximum SNR you want for your link. You're going to have to take the maximum EIRP, that's effective isotropic radiated power, that your transmitter provides, and you just have to give the system enough system operating margin or fade margin so that it stays reliable. So all of this is a condition of your Part 15 grant. In other words, you can't take a low-power device and add an amplifier to it unless it's been certified as a system solution. That's what we did. We took our 2.4 gigahertz .11b, .11g devices, married them with an amplifier, and sold it as a system. So those are considerations. This is why most telcos and cell companies avoid license-free band. We could never really sell to the Verizons and the Sprints and all those other telcos because they will pay the extra expense to get a licensed microwave link to protect them from interference to ensure reliability. They're all about reliability, and I can't blame them. And if they put up a 5.8 gigahertz link and then a couple of months later somebody else puts up one on the same tower that could get interference, they can't tolerate that. So they will pay, because they got the money to do it, for licensed links which will protect them from interference. But there are technical solutions that can virtually eliminate the risk and ensure reliable links. For example, going on the 24 gigahertz band. Your range is short, but the signals are so focused because of high gain dishes, the likelihood of getting interference on 24 gigahertz and even 60 gigahertz and higher is virtually nil. So there are things you can do to ensure risks. In fact, one guy put them up and it was getting interference on 5.8 gigahertz. He changed channels and went from vertical to horizontal polarization, interference gone. So there are things you can do if you have knowledge of the technology. So UNII, I mentioned, stands for Unlicensed National Information Infrastructure. I mean, only the FCC could come up with a name like that. Unlicensed National Information Infrastructure. This is where Wi-Fi lives, but the protocols do not support long range, even if you have strong signals, good SNR, because 802.11 AN and AC, there's a lot of non-Wi-Fi equipment available for outdoor use besides the specification. That's why I said if it doesn't say Wi-Fi, it's not Wi-Fi. And there are a lot of people out there companies out there that make non-Wi-Fi equipment for point-to-point and point-to-multi-point use. So we have the low UNII band I mentioned earlier, 5.15 to 5.25, indoor use only, 4 watts EIRP, point to multi-point. But on point-to-point, you could do up to 200 watts EIRP. That's plus 53 dBm. You can really haul with that. Likewise, the UNII midband is 5.47 to 5.725, indoor and outdoor. But you've got to have equipment that supports dynamic frequency selection or radar avoidance. In other words, if it sees a radar signature of some sort, it has to shut down or change frequency. Then we have the upper, which shares the band with the ISM band, 1 watt transmit power output, and virtually unlimited EIRP. You can put like a 36 dB gain dish if you got the room for it, and you can just go miles and miles with a very narrow beam. So that's the UNII band. So manufacturers get their equipment certified under higher power, according to the ISM Part 15 rules for 5 gigahertz, provides very long range lengths with high gain antennas, and here's some companies that make them with integrated antennas. This particular one, Air Fiber, I'm not supporting any particular one, but this Air Fiber one actually has full duplex. So they got 2 antennas, and they transmit on frequency A to this one and frequency B to that one, and gives you full duplex. And it's all integrated into one system. You just bolt this to the pole. Very, very exciting. I mean, it's really very useful and functional. So there are many non-Wi-Fi devices in this band, and many are used by wireless internet service providers to provide backhaul to the high sites. For example, wireless internet service providers with some high sites on mountains or tops of buildings, and then they would provide connectivity to their customers in that general area. As you can see, we have high-capacity Ethernet backhaul using point-to-point links, and then we have the base stations here talking to remote patients. Now, where would they do this? Well, I'm not going to do this in big urban areas because they got cable and DSL. But in a lot of rural areas, they still don't have cable, they still don't have DSL, and they don't want to use the local Verizon or Sprint wireless because they pay for every byte they use. So what these wireless internet service providers do, they offer license-free internet access, and they charge so much per month, and it's unlimited data because the connection's always on. So that's where they use wireless internet service providers offer these broadband internet access on the license-free bands. And from the high sites, they use 2.4, 5.8, or 3.5 and point-to-multipoint to connect to their clients, mostly in rural areas where there's no cable or fiber. They have their own organization with over 800 members called WISPA. And typically, this is what they do. They have the point-to-multipoint, bring internet, either wired or wireless backbone, and then they send it to all their customers. Put a dish antenna, something like that, to point back to the base station. That was our main customer, by the way, because when we were doing our stuff with YDI, there was no cable modem. There was no fiber. DSL was not even just barely coming out. Most of the time was the ISDN line. Remember that, 64 kilobits per second. You get 2 channels, get 128 kilobits per second. That was fast back in 1999. And so we came out with our outdoor wireless solution that enabled customers to give multiple megabits per second without getting a radio license with affordable equipment. Now, the license-free mmWave devices, 24 gigahertz band. It's just above the license, 23 gigahertz band, goes from 24.0 to 24.25. You have 250 megahertz of bandwidth. Point-to-point systems only. Several vendors offer links in this band with integrated antennas, which is really the only way to do it. You don't want to use a coax cable. Here's some examples of some of those 24 gigahertz antennas and integrated radios. And the state-of-the-art, again, I'm impressed with is this Ubiquiti AF24. They actually have 2 antennas. Because of the limitations on the EIRP, they'll have the transmit antenna here with the max EIRP they can give based on the FCC limitations for license-free, but then they have a bigger gain antenna for receive. And so this transmit antenna talks to the receive on the other side, and this transmit antenna talks to the receive on the local side. They use 0IF, from what I understand, as well. So it features 2 independent 2x2 MIMO, the 24 gigahertz integrated dishes. So they have MIMO, they're vertical and horizontal coming off one dish, and they get lots of throughput. They can operate full duplex or half division, hybrid division duplex. It's unparalleled speed and spectral efficiency in the 24 gigahertz band, license-free worldwide. Again, I'm not advertising to them. I'm just impressed with the technology, and it's something that if somebody has to do a point-to-point link a mile or two, I would consider this. Why does the FCC give the 24 gigahertz band away, for that matter, even the 60 gigahertz band? Why do they give it away for free? The answer is, it's the resonant frequency of the water molecule at 24 gigahertz, and hence it limits the range. And no one's going to buy that frequency band because it's hampered. So if we look at this chart here, we see on the bottom frequency gigahertz across the bottom, and the top is attenuation per dB per kilometer. So this is the attenuation dB per kilometer on the left, vertical. Horizontal is the frequency in question, and this graph shows the additional loss due to water absorption, because that's the resonant frequency of the water molecule. Everybody thinks that 2.4 gigahertz is the resonant frequency of the water molecule. That's why they put it in microwave oven. It's not true. It's the 24 gigahertz frequency. 24 gigahertz is the frequency, resonant frequency of the water molecule, not 2.4. Now, oxygen is even worse. Look at oxygen up here. Around, where is that? Oh, it's sitting at 60 gigahertz. And this is like 12 dB per kilometer, oxygen absorption. The H2O absorption is only 0.2 dB per kilometer. This is one of the reasons why outdoor 802.11d or outdoor 60 gigahertz links never going to work very far. More on that later. So the atmosphere has resonant frequencies that will attenuate the RF signals on top of free space loss. And note that the resonant frequency of water, 24 gigahertz, and oxygen, 60 gigahertz, are additional signal losses above the free space loss. At 60 gigahertz, this loss is quite significant. This is why the FCC has authorized it as a license-free band, because they could never give it to any commercial operator. The 60 gigahertz band is also called the V band. It's 57 to 64 gigahertz. It's got 7 gigahertz of unchannelized spectrum. 802.11d, by the way, channelizes it. The FCC also give this band away for free due to massive O2 losses in the atmosphere. No one would be willing to pay for it. Indoor uses, 802.11ad. Good application, wireless audio, video from computer set-top to TV, hopefully a replacement for your HDMI cable. And this is going to make the difference that they can now get permission to use HDMI interfaces, and they also have a standard 802.11ad, and now people can get on the bandwagon and start making equipment that's compatible from one manufacturer to the other. For outdoor 60 gigahertz, you can still do it, but oxygen absorption assures short range. Rain fade ultimately is the limiting factor, by the way. So in 2013, the FCC allowed more transmit power from plus 40 dBm to plus 82 dBm EIRP for devices using an antenna gain greater than 51 dBi. That's a little over 2 feet diameter, so it's not that big an antenna. And so you get 82 dBm. That'll go a long way to punch that signal through. And these long-range links use very narrow beam dish antennas, so that assures virtual no interference because it's almost like a laser beam. So in space, by the way, this is an interesting fact, military satellites use 60 gigahertz to talk to each other because no one can ever receive those signals on the ground because it's absorbed through the atmosphere. A little factoid there that I find interesting. Now, range of 60 gigahertz before the FCC increased the EIRP by 42 dB. That should not be dBm. This is the maximum range you can get for a 60 gigahertz link. So down here where I'm in central Florida, where I'm at right now, you can go 600 meters and get solid connectivity. Of course, you're out here in Denver, you can go about 1 kilometer at 60 gigahertz. Industry pressure made the commission realize that more transmit power is needed to overcome the oxygen absorption, especially the rain fade losses. That's why they increased it. So the compromise was narrow your antenna beam width in order to get the higher EIRP. We also have license-free band at 72, 80, and 90 gigahertz. This is called the E band. 71 to 76 gigahertz, 81 to 86 gigahertz, and 92 to 95 gigahertz. point-to-point link only, and extremely high data rates, greater than 1 gigabits per second. There's no oxygen absorption. However, rain fade and free space loss is even more of a factor than rain fade was, because there is no rain fade. Sorry, let me give that to you again. There is no oxygen absorption issue, but rain fade and free space loss is what will kill you. Typically used for cell tower backhaul, or connecting buildings or cell towers over distances of a few miles if properly engineered. So here's the question though. Can your 72 gigahertz link take a 33 dB hit in loss when the rainfall is 3 inches per hour, like it is here in Florida frequently? That's the thing. You need a 36 dB fade margin, otherwise your 72 gigahertz link ain't going to work. And here's an example of what I'm talking about. If we look at this chart here, we have attenuation in dB per kilometer and frequency in gigahertz. This is the rain fade chart. So if we take a look at about above 10 gigahertz, we start to take rain fade into account. Note the log scale, it's on the bottom, and that the precipitation is in millimeters per hour, and a millimeter is just a trace precipitation. So let's say it's 6 gigahertz, for example, and 100 millimeters per hour, that's 10 centimeters per hour. It only adds 0.6 dB loss. Let me illustrate that. So we have 10 gigahertz, and we're doing 10 centimeters per hour coming down on this graph here to 6 gigahertz, and we're just right about here. So we really get virtually no loss at 6 gigahertz. However, at 72 gigahertz, now we're way the heck up here, 50, 60, 70. We go up here like this at 72 gigahertz, and we come over like that, and now we're getting 12 dB per kilometer on top of free space loss. That's significant. So when you do a 72 gigahertz link, you really need to take rain fade into account. Why? Because the raindrops are now about the same size as the wavelength of the signal, and it just scatters it. At 6 gigahertz, the raindrops are tiny compared to the wavelength at a 6 gigahertz radio signal, so it really doesn't do a lot of scattering. But when the obstacle, namely a raindrop, is about the same size as the wavelength, it'll scatter it and absorb it. So the next interesting thing is white spaces on UHF TV channels, spawned from the FCC's desire to make VHF and UHF bandwidths available for wireless broadband communications. So they have the unused TV spectrum. They call it TV white spaces. They adopted the rules under Part 15 to allow unlicensed radio transmitters to operate in the broadcast television spectrum at locations where spectrum is not being used by licensed services. Why not? So this rule allows for applications similar to those used in 900, 2.4, and 5 gigahertz UNII band. The FCC has not dictated specific modulation or protocol requirements for this band, allowing the white spaces to employ a wide range of device and applications, just like unlicensed basis for Wi-Fi. However, they are very restrictive emission levels near the edges of the band, probably more than they needed, thanks to the National Association of Broadcasters, who want to protect the adjacent channels. That limits their air data rate to about maybe 3 megabits per second, which isn't so good these days. 10 years ago, not so bad. These days, too slow. While propagation is great non-line of sight, this limits the air data rate considerably, making it not so attractive. The FCC also ensured incumbent TV band spectrum users, these are broadcasters, public safety, registered microphone users, etc., have priority over white space operation. So those cordless mics you see when people run around on stage and on TV, they operating in the unused TV channels, and they have priority on these spectrum. Great RF spectrum, but not a lot of activity in these bands. That's why you haven't heard much about it. Here's something new that's come out. This is our final topic. The Citizens Broadband Radio Service, CBRS. This is a shared wireless broadband use of 3.55 to 3.7 gigahertz, or 3550 to 3700 megahertz, 150 megahertz of spectrum, established last April. It's found in Part 96 of the FCC rules. The new band is designated to support activities including small cell deployments, fixed wireless broadband devices, something the FCC calls general consumer use, and like CB, the lesser requirements attached to the FCC-approved communications equipment, meaning there's no requirement for individuals, users, to obtain licenses, even for commercial use. I say 10-4, good buddy, on this band. That was real interesting until last month something came out. That's even more interesting. Let's see, before I get to that, let's see, there's three-tiered authentication, incumbent, priority, general authorized, and most of the WiMAX equipment deployed operates in this band. But this is the interesting thing, which could be the mover and shaker. Recent news, August 2016. A half a dozen wireless heavyweights announced a partnership to boost LTE-based offering using the shared spectrum of the 3.5 GHz CBRS band. What users were they? Qualcomm, Nokia, Intel, Google Access Technologies, Federated Wireless, and Rutgers Wireless unveiled the CBRS Alliance to develop an ecosystem centered on the CBRS band. The new group said LTE-based solutions in this band using shared spectrum can enable both in-building and outdoor coverage and capacity expansion on a major level. And as you all probably know, running out of spectrum for the cell bands, and this would be an opportunity for this band, which just came out and no one was really using it yet, to have some big names behind it, pouring money into it to make this band work. The interesting thing, though, is that they have lots of hurdles to overcome, not the least of which is prove the technology works, and then get it into iPhones and Android phones, because they currently don't have the ability to operate on this 3.5 gigahertz band. So they've got to really prove themselves that this is a good band, that the technology works, and that, hey, maybe the iPhone 8 may have this 3.5 gigahertz CBRS band, and when you walk into a building, you are now connected to a microcell connected to the network that's on a 3.5 gigahertz band. Yeah, this will be interesting to see how this all pans out. So that really concludes all the material I wish to present. Who's got questions?
Hi, Mike. Yep, we got a few questions here. So the first question is, why haven't we heard much about broadband device wireless services in the white spaces?
That's a good question. A company called Spectrum Bridge set up a database to ensure that certain incumbent users are protected. And this TV white space communicate this database, get a list of available. However, the available spaces vary over time depending on and the equipment has to limit what channels they can operate on and have to be able to switch channels. But here's the problem. They have very restricted power levels at the edge of the channels, and Carlson Wireless products were certified by the FCC for use with Spectrum Bridge on white spaces back in 2004. Better applications developing in other nations, not the U.S. But here's the problem, though, is they are only authorized to use as an experimental license. They cannot make money or get paid for the service that they're providing. They need to get FCC approval for this and get in order to use this band for commercial purposes and make money. And they haven't done so yet, as far as I know. And that really, the fact that their air data rate is not so great, and the fact that they're running experimental licenses, I don't know anybody else other than Spectrum Bridge working on this band.
Okay.
Other questions?
Okay, next question. Can unlicensed devices with modular approval be incorporated into a device without marking the FCC ID outside the device?
Technically, no. You don't need to put the whole FCC Part 15 warning on there, but you do need to have somewhere just the FCC ID number if you're using an embedded Part 15 certified device. So the answer is you don't have to put the whole warning in. You can have to, that says you have to cannot cause harmful interference to licensed users, and you must accept any interference. All that doesn't have to be there, but you need to have the FCC ID number on there with statement that it's contained, an FCC ID number, blah, blah, is contained inside.
Okay. Let's see. Next question is, considering the limited range in the 60 gigahertz band, would this be a good choice for linking with isolation, patient, and operator areas of medical devices?
I wouldn't think that's a good idea, and here's why. Because the range is so limited, and I don't know what the real application is the question addresses, but you do not need gigabits of data throughput for most of these isolation patients. I would look at something in the low-cost 5 gigahertz band, because your range is probably going to be yards through hospital walls, I'm presuming. And you probably, I don't think 60 gigahertz would be good because of the attenuation through walls. I think a 5 gigahertz band would probably be a better solution.
Okay, I've got another question here about that 60 gigahertz. To extend the 60 gigahertz range to more than a few yards, could PoE devices for residential use, such as an AC plug-in Wi-Fi extender, be a potential candidate for utilizing the 802.11ad technology?
Yes, absolutely it can, but the jury's out to see what kind of range we're really going to get. For example, in my house, I'm running a 2.4 gigahertz cable modem with integrated antennas, and when I get to my wife's office at the other end of the house, the signal level is kind of weak, and that's at 2.4 gigahertz. At 60 gigahertz, the range is going to be marginal, and if you put a wall or two in between, it's not going to be effective, I don't think. So I think we're going to have to see how 60 gigahertz really plays out. I personally think it's just going to be short-range devices. You know, again, spitball range, but you can shoot, you know, spitball in a straw is probably the max range you're going to get at 60 gigahertz. That's my prediction.
Okay. Looks like I got one more question here. Can you provide some insight on common issues encountered when using broadband devices and how to resolve them?
License-free broadband devices, yes, I mentioned that earlier. The number one issue you're going to get is typically interference if you're on 2.4 for sure, and then 5.8 gigahertz. It's interesting because there is a company coming out that has already this developed on 2.4 gigahertz. They're running Internet of Things, and they're running 2.4 gigahertz spread spectrum, but very narrow bands, like 1 megahertz of occupied bandwidth. And they're doing direct sequence spread spectrum with huge processing gain because they're only transmitting kilobits per second. So they've got something like 30 dB processing gain on the 2.4 gigahertz band, which has a Wi-Fi access point every 100 yards or so. You can't go down in an urban area and not see 3 or 4 or 5 2.4 gigahertz access points anywhere you go, just about. And I spoke with them and I said, how in the world are you getting such good performance from these low-power things like power meters, water meters, etc., on that 2.4 gigahertz band? And basically, I had to pull it out of them, but it's basically because they're running very high processing gain, you know, megahertz of bandwidth, but only kilobits of data, and so they can overcome interference from other signals. There's an example of using the ISM band, not Wi-Fi, how to overcome interference. But typically on point-to-point links, in the 5 gigahertz band, for example, that's where a lot of point-to-point links go that many, many miles, is you use higher gain antennas or high gain antennas and change channels if necessary, or rotate the polarization from vertical to horizontal. And that's what customers have used to get the systems back and working. But for me, for short range, I'd go to 24 gigahertz, and then I would not have to worry about it. Pick up any other questions? If you're speaking, we can't hear you, Christina.
Hi. Sorry about that.
Okay.
So, we didn't have any more questions come in, so basically, I guess just real quick, I'm going to go over a few things about upcoming training from Washington Labs Academy. The link that I have here on the screen connects you to our Academy page, and you'll find information on all of our webinars and resident courses, and they're available in a variety of topics. Here we have some Washington Labs Academy training webinars and courses. The next product safety webinar is on October 18th. That's laser facility safety for MIL 461G. The RS 101-102 session is on October the 19th. And environmental session 10 is on October 20th, miscellaneous tests. And the next wireless series session is December 6th on Far East wireless approvals. Also have for IEC CISPR FCC testing, session 6, October 11th, and that's on EPRI TR 102-323R4. So if you want to check out any of our previous webinars, please note that all are available for purchase from the WL Academy website. We also provide customized training at your place or ours, and webinars are available in a multi-part series so you can mix and match them. You can take one session or a few from any combination of available webinars from any multi-part series, or sign up for a complete offering of the Academy training courses happening throughout the year. Please be sure to visit the Academy training page to check out the latest training course topics and dates. We'd also love to hear from you with suggestions on future topics we can present. So let me check real quick here and see if we have any other questions that might have come in. Looks like we don't have any more questions. So, Mike, I think that's going to wrap it up for today.
That's good. Thank you very much for folks listening. I hope there were some gems in here that you found interesting that might be useful to you. You probably know most of it already, but some of the new stuff coming out hopefully will have been informative for you.
Absolutely. We appreciate everything. We appreciate your time very much.
Glad to do it. Look forward to the next one.
Awesome. So that'll conclude today's webinar. So on behalf of myself and Washington Labs Academy, I'd like to thank everyone for their attendance. And at this point, I'll go ahead and end the event. So enjoy the rest of your day, everybody. Bye-bye.